fundamental theorem of calculus. Sounds a bit ominous, right? The fundamental theorem of calculus, okay? It actually is very important. It's a very important theorem. And there are two parts to it. We'll do the first part, the first half, the second part, the second half. Okay. And it's basically the stuff that we talked about during that exploration when we did the accumulator function, and we found that the derivative of this guy was equal to f of x. This is what we found. Remember that, right? We did the shading thing, and we went like this, A to B. You guys chose an x, and we shaded it. We found out that the incremental increase would have been f of x, right? If we do the derivative of that, right? We talked about that. Okay, so this is part one of the fundamental theorem of calculus. So you go to page 302, there's a green box there that basically states that. Okay. So then in here they also talk about the capital F of x, right? What is capital F of x really? In your own words, what is it? What is f of x? This is the antiderivative, right? What is the antiderivative? Okay. And so we said that this is going to be equal to this guy. Okay, this guy right here. Okay, this guy right here. All right. Did that, we do this, we get this. So that is it. So we've talked about it in theory, how this works. Okay, so let's kind of put some numbers to this and see how this actually goes. Okay. So let's go straight into example number one. See how this works. Example number one says, find negative pi, and you are given this as what? Cosine t dt. Okay, so we want to find this. So what is this? Anybody tell me? Based on what we know that, right? We know that the part one of the FTC said that d of dx, a to the x, f of t dt was equal to f of x. So do we have everything here? We have everything, right? So what should this be? Which would be cosine x, right? Just cosine x, right? The answer is cosine x. Right? It's cosine x. That's it. We're done. What if I change this to be this? Still the same thing. Okay? Right? What if I changed this? Still the same thing, right? Because these are dummy variables, right? And they can be anything except for, it can't be x, right? Because we're using x in our intervals right here, okay, right? So it can't be those, right? Okay, so it's as simple as that. And, oh, there's another one to it. I'm sorry, thought we were done. I guess we're not. 1 plus t squared, 1 over dt. It actually is 0 here, isn't it? Yeah. So how do you do this? This would be equal to 1 plus 1 over x squared, right? I'm just basically regurgitating what was here and whatever I'm putting the x into right here, just like I did with the cosine one, right? Okay, so that's that. Let's go to example number 2. Example number 2, find dy dx if y is equal to that. So we are doing 1x squared cosine t dt d dx. Right, that's what we're doing? Is that correct? So we said 1 cosine t. Okay, all right. So I'm going to do this. What is different from what we have over there? What is going to cause us some problems, or could cause us problems here? Squared, right? This guy right here is different. It's not x, right? If this guy was x, I would be fine, but it's not, right? So let's go ahead and make a substitution and say x squared is equal to u. Now let's go ahead and take the derivative. D, so we're going to, if I take the derivative, what am I going to get here? I'm going to get, do that again. 2x, then I have to do the chain rule, right? Dx, right, is equal to du, right? So what can I say here? dx would be what? What can I change that to? If I want to change that to du, right? So dy dx, which is what we're trying to find, is the same as dy du du dx, right? What is du dx here? And what is du dx? 2x right here, right? 2x, right? So if I go ahead and change this to u, right? And then this needs to be u, right? dy du or dy du, right? Then I have to multiply it by this, right? du dx, which is 2x. So what I would have found was what? I would have found cosine x squared, right? But now I have to multiply that by the 2x, which is basically what? It's the chain rule, right? Exactly. It's the same thing as a chain rule. So you just do the substitution and then you do the chain rule on that. Okay? All right. So it's 2x cosine x squared, right? Okay, there you go. So let's go ahead and that's good. Let's go to example number 3. Example number 3, we have a y is equal to, from x to 5, then we have 3t sine t dt. We're trying to find dy dx. So taking the derivative of this. So what's the problem here? What's our problem here? We know that the first part of the theorem says this. So what's our problem compared to that? What's going on with this one? He's in the wrong spot, right? This guy's in the wrong spot. We need this guy to be up here, right? So how do we do that? We just put a negative to it, and we just change these, right? I can do that. Right? Remember that a to b, f of x was equal to negative from b to a, right? And that was, where is that on? Page what? 6.3, page 293, number 3. Okay, it's page 293, and the rule number 3 will allow us to do that. So if I take the derivative of this, what am I going to get? Now I'm good to go, right? So it's just the derivative of this is going to be equal to negative d dy 5x 3t sine t dt. So now I'm good to go, right? Negative 3x sine x. That's it. All right, so the only true manipulation that we did was flipping the limits from x to 5 to 5 to x. Okay. And let's go and do y, not y2, b, I guess b. In b, we are faced with a different problem. We have y is equal to 2x to x squared dt, right? Now what's our problem here? Okay, x squared itself is a problem. What else is a problem? I have x's in both sides, right? But I only want x's in one side. I can't have them in both sides, right? So the way we get around this is we're going to go and say this is the same as minus you see what happened there? I said from here to here, so I'm going from 2x to x squared, right? I'm going to go from 0 to x squared and subtract from that 0 to 2x, because that's what I'm looking for right here, right? Does that make sense? You get that? Right? So the 0 is really, it doesn't kind of matter, right? It could be any number here, right? Okay. So what do we get? We're going to get, if I take the derivative of this, now what do I get? I take the derivative of this, which is going to be what? 1 plus 2 plus e to the x squared. Then what do I have to do? The chain rule. So what am I going to get? Multiply this by 2x, right? Then I'm going to subtract it. From that, I'm going to subtract this guy, which is 1 over 2 plus e to the 2x. Then again, I have to do the chain rule. So there's a 2 there. Okay? Kind of, not so easy, not so easy. Right? Real tricky. Let's see. Example number 4. Let's do example number 4. Example number 4, we have constructing a function with a given derivative value. Find a function that, so in this, they're giving us the other way around, and we have to cobble something together that is such that it makes sense. So they're giving us this. We also know that f of 3 is equal to 5. Okay? So since I know this, I can say that y is going to be equal to 0 to x tan t dt. Can you see that? Right? Because if I take the derivative of this, I will get tan x. Right? However, I also know this. So I'm going to have to do some manipulations here. Right? I'm going to go ahead and say this is 3. Right? So when I put 3 in here, I'm going to get 3 to 3, which means what? This would be 0, right? I would 0 this out. But it has to be 5. So I'm just going to add the 5 there. Why can I do that? Because when I take the derivative of this guy, what happens to the 5? It goes away. I could put 5,000 here and it would still work. I could put any constant here and it would work, correct? If I did not have this restriction, right? But now that I have this restriction, that's where the 3 comes in, okay? Put the 3 over here and putting the x up here, because it zeroes this out. And then just leaves me with 5. So this is the condition that gives me the value of the constant. Okay? That makes sense? So there's that. We've got that. So we were able to cobble that together. Okay. Okay, so there's a paragraph in the middle of page 305. It says, although the solution to the problem in example 4 satisfies the 2 required conditions, you might question whether it is a useful form. So does this really help you? Right? Does this make any, what good is this for you? I guess is what they're saying, right? Okay. It also continues to say that we will see in chapter 7 that we will do this and we will find that the actual solution here to this guy here is going to be y is equal to the log of, what is it? Actually, it's the natural log of cosine 3 cosine x plus 5. Okay. Okay, so that is the actual, so this, which would you rather have? Would you rather have this solution? Or would you rather have this solution?
No.
This one?
No.
This one? Why would you rather have this one?
It's simpler.
It's simpler? This looks simpler than that, doesn't it? I can at least graph this one, right? It's easy to graph. I could graph this, right? But I would have to use what? Yeah, my calculator. I have to do the FNI and T and all that good junk, right? Okay. So this is actually the preferable solution. Okay. So let's go ahead and look at the graphing the solution. Okay, I'm talking about the FNI and T, blah, 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 blah. Okay, we can even use int to graph the function. We already talked about that. Okay, so we're good with it. I don't think we need to go any further up that one. Okay, so we'll stop right here. We'll stop right here, and we will do the second part, the evaluation part, later on.